When you concentrate too much mass into a single structural point, the entire system becomes fragile. A localized failure forces the whole structure to buckle. In Android development, this exact structural failure happens inside our screens. Consider an interactive video call app built with Jetpack Compose. You have a LazyColumn rendering a feed of participant cards. You tap the first participant card to pin their video feed to your screen, and you slide their specific volume down to 20%. The UI reacts as expected. Then you scroll down the feed. When the 8th participant card enters the viewport, it appears already pinned. Its volume slider is already set to 20%. The state of the first user has bled directly into the 8th. This state bleeding bug is the direct result of the God ViewModel anti-pattern. When a single screen-level object manages the individual volume, pin state, and network status of every subcomponent, unrelated elements begin to overwrite each other. For years, developers were forced into this architecture because ViewModels could only be scoped to rigid navigation entries or full activities. There was no clean mechanism to give an individual composable its own isolated logic. The common first pass is to push the standard ViewModel call directly into the LazyColumn row composable. On paper, this should allow each row to instantiate its own isolated logic engine. But the ViewModel function relies on local ViewModelsToreOwner.current to resolve its instance. The closest active store owner is still the parent nav entry at the top. The row's request travels up the compose tree and resolves at the nav host level. The nav entry store only holds one participant ViewModel. The factory runs once, and every subsequent row receives that same instance back. 12 rows are now sharing a single brain. You can force multiple instances by providing a unique key for each row. The duplication stops, but you introduce a memory leak. Scroll a list of 1,000 users, and the nav entry accumulates 1,000 ViewModels. Since the screen hasn't popped, the store never clears them. Without a way to intercept and localize the ViewModel store lower down the compose tree, true independent component architecture remains impossible. Lifecycle 2.11 provides the interceptor we need, rememberViewModelStoreOwner. This specific API mints an entirely new ViewModelsToreOwner that is scoped exclusively to the actual call site of a specific composable. We simply wrap our row content in a composition local provider and swap out the current owner for our newly minted one. Now when the row asks for a ViewModel, it queries its own private store. The resolution path now stops at the component layer, inheriting parent factories for things like hilt injection. Lifecycle triggers map to the component's composition. When the card enters the viewport, the ViewModel initializes. When it scrolls off screen, the localized owner clears, destroying the ViewModel. This creates a sealed boundary for side effects. Any active polling logic or coroutines running inside the component's ViewModel scope are accurately and instantly canceled. Developers can now enforce granular memory management, allowing ViewModels to live and die in perfect sync with specialized UI blocks. This aggressive memory management creates a new problem. If the local ViewModel is destroyed on scroll-off, any local user state resets when the item scrolls back into view. You expand a text block and you scroll down. When you scroll back up, the text is collapsed again. The user's interaction was wiped because the UI state died with the ViewModel. To fix this, we have to persist specific data variables outside the ViewModel's immediate lifecycle boundary. We construct a durable state vault by pairing a saved state handle inside the ViewModel with a savable state provider keyed to the item's unique ID. Watch the sequence. As the node leaves the screen, the savable state provider snapshots active variables, dropping them into a per-key bucket. When the node re-enters, a fresh ViewModel is minted. It reads from that external provider, repopulating local variables to render exactly as left. Because this isolated, per-item state slice delegates directly to the parent nav entry's saved state registry, it easily survives a total process death. True granular architecture requires a dual approach. We destroy the logic engine to save memory, but we archive its data to maintain a seamless user experience. Transient items in a list should die off-screen, but durable navigational items like tabs in a HorizontalPager have different requirements. If we use rememberViewModelStoreOwner on a search tab, swiping away causes the tab to leave composition, wiping the user's active search query. When the user swipes back, they face a fresh, empty ViewModel. For these cases, Lifecycle 2.11 provides a separate tool, rememberViewModelStoreProvider. A provider manages a discrete set of child ViewModel store instances. It acts as an artificial holding area, keeping specific child ViewModels alive as long as the parent component remains active. We hoist the provider above the pager, supplying it to each tab with a unique key. Swipe away, the UI disposes, but the store is held by the provider. Swipe back, the provider recognizes the key and returns the exact ViewModel, preserving your search. Hoisting the provider decouples the ViewModel's lifespan from the visibility of its UI component, securing state across navigational gestures. Now that scoping is decoupled from nav entries, developers can choose whether to maintain state at the screen level or distribute it into the UI tree. This introduces a new engineering trade-off. You are weighing the simplicity of one screen-level ViewModel against the modularity of multiple specialized ones. The professional rule of thumb is to isolate heavy, distinct interaction states, like participant controls, but leave simple read-only list data to the parent screen. Lifecycle 2.11 allows Compose to enforce architectural boundaries directly at the component level. This raises a question for your codebase. Do you prefer sticking to official Android X scoping mechanisms, or moving toward pure Kotlin ViewModels for multi-platform consistency? Let us know in the comments below. Mastering these granular lifecycle scopes provides the control needed to build highly responsive, memory-efficient interfaces as Compose apps grow in complexity.